We have unbounded areas when we have vertical asymptotes and when we are integrating to infinity. So the example up here is we have a vertical asymptote, and this area in here is becomes unbounded, and we have this unbounded area going up to infinity. We also have unbounded areas when we have integrals that go to infinity. So we start at some point A, and as we integrate along here, this is unbounded because we're going out to infinity. Now, integrating these unbounded areas are a problem because we're not allowed to go to where the boundary point is. So for this, in this case here, at x equals 0, we want to integrate to x equals 0, but we're not allowed. Okay, so this 0 is a problem when we write the integral. Same with the integral here when we write this integral. This integral to infinity is a problem because we're actually not allowed to go to that point of infinity. Now, when we're going to define an improper integral, and we're going to define this using limits. And it's important to understand that for the most part, a limit is just a formal way that we evaluate these integrals. If we actually just integrate them normally, for the most part, they will just integrate the same, and we'll get the same result as we do when I show you more formally with a limit. We do have to be we have to be especially careful though, because although the blue part of this is true, we can integrate normally. If we integrate across a vertical asymptote as part of our bounds, then that's a problem. We get invalid results. So we have to be careful with that. But otherwise, we just have to write this formally using a limit because we're going to places that we're not allowed to go. And in these two cases here, we're not allowed to go to the 0, which is a vertical asymptote, and we're not allowed to go to infinity for the other one. Okay, so we're just going to now evaluate these using a limit. So to do this, we do this. So looking at the first one, we're going to now use a limit because, again, understand why we're using a limit. We're using a limit because we cannot use that 0 as a boundary point because that 0 actually doesn't exist. So we're going to do it like this. We're going to say the limit as t approaches 0. And now that we've defined t as going to 0 instead of 0, we're going to say that we're going to integrate from some value of t to a value of 1. Now, because this is a one-sided limit, we're integrating on the right-hand side, we have to make sure that this is a one-sided limit. Okay, so when we're doing these improper integrals, we have to set these up as one-sided limits when we go to the asymptotes. And I just write the exact same thing as I had before. So at this point, because I have a limit, now I can actually evaluate this integral. So I'm just going to integrate normally. So I'm going to end up with log x, or in this case, and then I'm going to go from t to 1. And because t is going to 0, I need a limit to show that t is approaching 0. And again, it's from the positive side. So when I do that, I'm going to evaluate this limit now. I'm going to plug in my t value. So this is going to look like this. The limit as t approaches 0 from the positive side. Now I plug in ln 1 minus ln of t. And because t is approaching 0, it's going to, log of t is going to negative infinity. So if you kind of think about the log function, I'm going to 0 from this side is headed towards negative infinity. So therefore I get 0 minus, this ends up being negative infinity. So my area that I evaluate is going to be equal to infinity. So what that tells me then is that area that is bounded by the vertical asymptote and some point at point 1, that area is infinite. And we would have gotten the same result if we just plugged in 0 and 1 into the integral. However, it is important that we use a limit because in calculus, we really shouldn't be going to 0. If we're going to 0 that doesn't exist, that boundary actually doesn't exist at 0, we should use a limit. The same holds for going to infinity. For this one here, we're going to just set this same thing up, limit as t goes to infinity. I'm just arbitrarily choosing a variable t, and this is going to be the integral from 1 to t now, and then this is 1 over x dx, and I can then just anti-differentiate this, so I get the limit as t approaches infinity, and I end up with log of x from 1 to t. I plug in my 1 to t in, so I get log of t minus log 1. Log 1 is 0. Log of infinity, when I plug t as infinity, log infinity is infinity minus 0. So the answer is infinity. So the area, this unbounded area out here, this unbounded area all the way to infinity is going to be infinite. Okay, now this happens to be infinite, but there are many unbounded areas that are actually finite.